So how do we know what the structure of the magnetic fields are in the jets? And so I quickly pulled up this beautiful plot from Robert's work. And when we look at this jet, 3C31, well, it's a magnificent jet. I just started looking at it earlier because Martin asked me a question. He said, if I model this, then everything is solved. So I got really excited because if Martin says that, then I should do it. Yeah, exactly. So I think that's great. So I'm looking at this, and it looks beautiful. So we see that there is a polarization signatures which are across the jet, and along the edge of the jet, they are along the jet. So how do we interpret this? So in my view, it means that the magnetic field is almost purely toroidal. There was a paper by Nadia Zakamska. Mitch Begelman was there, and the authors also, I don't remember who was the third author. Oh, Roger, right. Of course I know. Just testing if everybody is up and running. So that paper makes a really good point. If you take a jet that is purely toroidal and you look at it from different angles, let's imagine that we have purely toroidal field loops and we're looking sideways. Then all the electrons will be going on orbits around these toroidal field loops, and we're going to see polarization along the jet, purely along the jet. But if we look at any small angle, then we're going to see polarizations that are different. Imagine you have a ring here. So at the top and the bottom, if the jet is like this, so meaning on one edge and the other edge, we're going to see magnetic field lines that are parallel to the jet, meaning polarization that's perpendicular to the jet. And that's what we are seeing. Or actually, are we seeing the opposite thing? Did I mess it up?
There's a B field backwards.
So you're right. So am I right or am I wrong? Okay, so this is good. I'm starting the discussion. So now take it from there. So am I right? So what's the structure of this magnetic field?
Well, I mean, I think I agree with you that the toroidal component is dominant, but the argument is subtler than just looking at the field vectors. You could get that field structure in a number of different ways. One of which is to have what's essentially a disordered field with no longitudinal component in the center and a parallel field shear layer. And in fact, I wouldn't be particularly surprised if when the northern jet does its kink, you can see that the polarization degree is enhanced on the outer edge of the band. That might well be due to shear. As it happens, we've done more detailed modeling of the inner jets, I mean the straight bits in that picture, and we concluded that the dominant component on the outer straight bit of the jet was indeed toroidal. So I mean I think that statement is correct, but it's not obvious from looking at the picture. And I might as well make the obvious comment at this point. From the synchrotron radiation at high frequency, you don't know whether the field is going one way or the other way. Don't know whether it's going forwards or backwards, so you've lost the sign. And that's what makes this a somewhat ill-posed problem.
So how do we know if this is perhaps a regular or irregular field? Is there a way to probe this?
It's very difficult without Faraday rotation or some other signature to say whether the field is, I mean, we can say it's toroidal, but you could perfectly well say, you know, it was toroidal with reversals or it was ordered toroidal. Now, I suspect that the component is probably ordered, the toroidal component, but the poloidal component isn't in this particular case. I'm trying to remember exactly what we think the field ratio is here. I mean, I think the poloidal component, even sort of the end of the straight bit, is non-zero. Back a bit, down a bit, there. It's in our 2014 paper, so you can look it up. But what you can do as a diagnostic in these things is you can look at the transverse profiles. And what that tells you, if you think about the distribution of magnetic field angles to your line of sight on the left-hand side of the jet and the right-hand side of the jet, if those are different, that means that the emissivity will be different on the two sides of the jet because the emissivity depends on sine theta in the rest frame. And so if you see a systematically asymmetric profile in either total intensity or in polarization across the jets, then that's a signature that there's something that's causing the distribution of field angles to your line of sight to be different on the two sides. That's what you expect for a grand design helix. And that's why we don't think in these particular regions of kiloparsec scale jets that the fields are grand design helices, because we've looked rather hard at the transverse profiles and they're pretty symmetrical. That doesn't say anything about parsec scales, but it does say that on kiloparsec scales, that's not a viable option. Now, there are plenty of other field configurations that satisfy the constraint that I just enunciated. You could have a double helix. You could have a helix going one way on, I mean, it's rather silly, but in theory it satisfies that constraint. But those are the constraints that you can get without invoking any Faraday rotation, I think.
Any other comments here?
I'll try. Okay, hi. Can I try a question and a comment? And they're actually linked, I think. The question is, I suppose, to Robert. I think this is 3C31, and it comes out of NGC 386, I think, which has a companion galaxy next door. Do you believe, as we once did, that those kinks are due to orbital motion of the galaxy, or do you believe they're just an instability that would be there without the companion?
I don't think they're due to orbital motion. I mean, I think the numbers that come out for the densities and speeds of the jet are very low. They might well be due to sloshing motions in the group. I mean, so the other element of this, along with the companion, is that there's quite an extended group of galaxies with an X-ray halo which is centered on NGC 383. It could well be that, there's gas sloshing around in there, as well as possible instabilities in the jets.
Sure, but it could be that this particular bending is caused by extraneous features rather than some sort of local instability.
Yeah, I mean, I don't buy the sort of the ballistic model, but certainly I also don't have anything to say against, the galaxies are moving with respect to each other and churning the gas up.
Okay. Well, then the comment was, I think, is even though we don't have Faraday rotation and can't measure the sign of the toroidal field, if there's a dominant toroidal field along a straight stretch, and unless it's lying in the plane of the sky, then you ought to see the polarization go down at a field reversal. There's a field reversal, and this may be telling us something that's terribly important, which is, I would otherwise regard as an open question, that the toroidal field always has the same sense, the current always has the same sense flowing along the jet on these long time scales, which is then feeds back into theories of how the magnetic field is made in the disk in the first place.
Yeah, I mean, we don't see, what we see is a sort of a continuous change from poloidal dominant to toroidal dominant. Once it's got toroidal dominant, we don't see any changes in that structure, which I think means there are no reversals within that.
That's a long time, because this is a slow jet, and the propagation time along the straight bit, at any rate, never mind what happens after that, is a long time in the accretion time scales.
Yeah, no, I would put money on the field not reversing in that stretch.
That is an awfully important conclusion, if true in general, for the theories of the origin of the magnetic field in the disk, because it says it's in some sort of dynamo process in the inner disk, which would almost certainly keep on reversing. It's really telling you about the field on the very largest scales in the accretion process.
Yeah, well, I mean, I can certainly say in the objects that we've looked at in detail, once the field gets to looking like mostly toroidally dominated, there are no sort of zeros in the polarization along the jet. There's nothing that looks remotely like that.
So where does the Faraday rotation come from? If we're looking at a jet, if we want to diagnose the jet, would it come from the jet or from the surrounding sheath?
Well, I mean, sorry, I'm monopolizing the discussion, but so cut me off if you want me to shut up.
We'll love you, so talking.
In this particular case, my argument would be that it's coming primarily from the group gas. The reason I say this is, I mean, firstly, if you look at the Faraday rotation pattern, it's quite chaotic. It's consistent, I think, with being a Gaussian random variable with a density profile superimposed on it. We've published some estimates of what this might look like. And there's a big asymmetry. There's a big asymmetry in the sense that the southern half of the source has higher Faraday rotation gradients than the northern half. And then we interpret this as simply being that the northern half, the approaching half, being on the near side and looking through less gas. It's not as simple as taking a spherical distribution and a plane source and integrating through it. You have to say that there's some cavity around both the northern and southern lobes to get the right sort of functional form. But the fact that you see this asymmetry and you see it consistently means that it has to be happening in something which has a scale size which is comparable with the size of half of the source as you've plotted it there. And that to me means it's plausibly in the group gas with, you know, holes where the cavities are. And I think that I can't see how you can get that sort of asymmetry with a sheath model or even with an internal model.
Asymmetry, you're talking about at these distances or somewhere here close?
It's basically there's a big change across the nucleus. I could probably find the slide, but I don't think we got time.
I was wondering from Denise's talk if you could, what was the size scale over which you were finding the toroidal field was essentially flipping sign? Because that might, you could explain that if the poloidal field switches, then presumably that's another model for.
Okay, well, what I was going to suggest is that I would actually quite agree with Robert, particularly given that we generally expect the toroidal component to become strong relative to the poloidal component as the jet expands and propagates out. That in the sort of picture that most of the measurements that we've been doing are on much smaller scales, on parsec scales. Okay, and
so if you had poloidal reversals on parsec scales, would that just average out on these kiloparsec images?
Say that again.
If you had poloidal field switches on your parsec scales, would that average out on these images?
Well, what I was going to suggest, rather than having the poloidal field switches, which I have a hard time imagining how they would come about physically, what I was going to suggest instead was, if you imagine that the sort of helical field generated at the very base of the jet of the sort that is shown in simulations by people like Sasha, and you imagine that maybe on the VLBI scales, there's still a significant poloidal field there together with a toroidal component, and we do actually see evidence of the sort of asymmetric polarization structures that Robert was referring to that could indicate the presence of a poloidal component. But by the time it gets out to kiloparsec scales, the toroidal component is completely dominant over whatever poloidal component was there, so that you have the hope of detecting a systematic toroidal component through Faraday rotation measurements if you can find a source where the ordered field dominates over the random components in the Faraday rotation, but the poloidal field is essentially negligible.
But the poloidal field initially is spun up to give the sign of the toroidal, right? So if you flip the poloidal, if the black hole's still rotating in the same sense, presumably it is, you flip the sign of the toroidal. So that would be the idea. That, yeah, the poloidal field's pretty much gone by that stage, but the sign of the toroidal field still depends on the initial flux of the.
Yeah, I mean, the
toroidal.
idea would be that the sign, I mean, in a simplest picture, I think that the sign of the toroidal field would be preserved all the way up along the jet. Why shouldn't it be?
Well, yeah, well, I agree, but I'm just saying that the sign of the poloidal field at the base near the black hole is determined in his simulations by Sasha shoving in a load of net poloidal flux.
Oh, yeah.
But there's no reason for that to be the source of the poloidal field. It
depends on how long the outburst is in some sense, because when the field flips the sign, that's when the jet will die for some time.
Temporarily.
And so I guess we could try and look for those things, and maybe those X-ray dips are those deaths or births.
I mean, the other thing I would just remind people, I know it doesn't seem to be very popular for reasons that I don't really fully understand because I'm not a theoretician, but there have been suggestions about mechanisms that would have the field, the initial field that's wound up, be somehow generated by the system rather than just being a random seed field. I mean, in that case, then you would not have the sort of situation that you're talking about, where you could have sort of a flip in the poloidal field and you'd have a null in between.
I think it's just completely not understood where the initial poloidal flux comes from.
I think that's a very good statement.
It
I think
comes
that's an
from
absolutely true statement. I think if we can actually make progress on understanding where the initial poloidal flux comes from, that supposedly is wound up and makes the whole launching mechanism, I think that would be really good.
Because you can get it from if it's from the MRI wind that essentially kicks off a kind of a magnetic, or kind of a Blandford Payne type wind out, you can just generate a poloidal field pretty randomly from just the MRI dynamo, or alternatively you can have a kind of a Sasha-like drawing in of a net patch of flux.
Let me pull a will here. I will pull a will, meaning I will propose something that you proposed yesterday for the origin of gamma ray flares. I think that both possibilities, both the turbulent generated large-scale flux and large-scale flux brought down from large distances, are possible. And the question is, how do we tell? And it's not clear. But I guess if we find a way of establishing that the same magnetic flux is threading the jet from the bottom to the top, then this is a really good indication that perhaps large-scale flux is dragged from large distances, because otherwise it's really hard to imagine how a mechanism can produce the magnetic field of always the same sign, even though I imagine that some mechanisms can do this, like
But also just make sure people realize that it has actually been demonstrated that the magnetic flux is conserved from the base of the jet to parsec scales.
Yep.
And this was used in order to measure the magnetic field strengths threading the black hole. You use core shift to measure the magnetic field strength at parsec scales, and then you go down to the event horizon.
I wasn't disputing flux conservation.
Sorry?
I wasn't disputing it was fairly ideal.
So we have Martin, and then...
Okay, so just to add to the observational comments, two things. First of all, if you look really close into that image, which we can't do, you will see that if you look really close into that image, right in the middle, where we can't see it, you'll see that the apparent field direction is parallel to the jet, not perpendicular to the jet in the middle. And that is also the field configuration that you see in FR2 type relativistic jets, typically. So imagine that you now had a high resolution image there, and you would see what I mean. You can't see it on this one, but it's there in Robert's pictures. It's there in pretty much every FR1. That throws a little bit of a spanner in the works for it's completely dominated by toroidal, unless you assume, and I think this is probably right, that in those FR2 type jets, what you're seeing is a shear layer, and has nothing to do with the actual field configuration. And so, for some reason, the true underlying field configuration of the jet is visible to us in FR1 jets, but it's purely shear layer in FR2 jets. I actually think there are reasons to believe that, but it's something you have to believe if you're going to invoke a single jet origin for everything.
When you're talking about FR2 jets, what distances are you thinking of?
Well, pretty much all of them.
Well, sub-parsec distances? You probably cannot resolve those.
I will abandon sub-parsec distances to other people, but.
Would you have a situation where the part of the jet that Robert has modeled similarly has a sort of relatively simple situation with the toroidal field? Okay. I mean, what if we distinguish between the inner part of the jet, which I think Robert was focusing on when he was modeling, and then further out when it looks like there's instabilities and disruption and stuff. I mean, it looks like the dominant. These are B field vectors, right? So it looks like the dominant B field in that part of that that Robert was referring to is actually perpendicular in the middle and goes parallel near the edge, which would be consistent with a toroidal field.
Once the jet starts bending, I mean, Robert really wants to come in here, but once the jet starts bending, I think we are very confused. But the inner straight parts of the jet, just focusing on those for a moment, show this switch over from basically parallel to basically transverse field.
Yeah, I mean, have a look at our 2014 paper. I mean, we actually do give our best estimates of the fractional components, longitudinal, radial, and toroidal in that. Forget the radial, there isn't very much. In fact, it is polloidally dominant, even at the base of the flaring region. And Martin's quite right. It is. The apparent field is longitudinal in the thin bit of the jet before that even starts, and we have no idea really what's going on in there because we can't resolve them transversely. But even after that, even when the jet starts flaring, the polloidal component is dominant, and I think it has to be a polloidal component with many reversals, not a. Yes, unfortunately, this isn't quite high enough resolution to plot. It's sort of within the first 2 or 3 vectors on that scale down there. Yes, I mean, so what happens is, on say a quarter arc second resolution image, what happens is you see a narrow bit of jet, faint bit of jet, and then it brightens and it flares out, and then it recollimates again. You can just about see the recollimation there. Where it first starts flaring out sideways is where we can first start transverse resolving it and saying something reasonably objective. At that point, all of the objects we've looked at are polloidal field dominant. So it happens even after the bit that Martin's referring to. And then there's a gradual transition to being toroidally dominant. I have a whole. In fact, I think I put it in my talk. There's a whole set of sources where we give our best estimate.
In the polloidal field?
Oh, I mean, in a shear flow, you can just sort of end up with lots of little loops.
Okay, so the polloidal field would be basically from shear then, and it's kind of an intrinsic.
Yeah, I mean, I mean, you know the basic. I'm sure we all know the basic argument. I mean, the transverse component of the field goes as r to the -1, and the polloidal component goes as r to the -2, modulo a Lorentz factor.
How does it work? How can you somehow get rid of the toroidal field at those large distances? Because
you're not getting rid of the toroidal field at large distances. I think the toroidal field is still there. What you've done is you've lost the ordered polloidal component, but you've got it back again through shear.
Have I lost the polloidal component, or have I lost the toroidal component?
No, you have not lost the toroidal component. The toroidal component is still there.
No, but initially near the black hole, I'm purely polloidally dominant. Then I propagate further and further out, and then I become toroidally dominant. Yes. And then you're saying at kiloparsec distances, I somehow become polloidally dominant once again.
From shear.
You need emissivity structure. That's the thing. I mean, if you have shear at the edges, but the edges are the only things that are emitting, or the dynamic emission, then you will see.
So the
field dominating. No, there's still a toroidal field in there.
Yeah.
It's a little bit hard for me to understand, but let's talk about this.
I mean, somebody showed the diagram from Beagleman, Blanford, and Rees, which actually has a picture of field loops evolving outwards, which I think is the picture that we have in the back of our minds here.
Okay. We have a co-author here, so we can interrogate him. So we had a question over here.
Yeah. So actually, it's more of a clarification that specifically focusing on subparsec scales. Are we saying that no matter what the structure of the magnetic field is, it's always going to be completely ordered, or is there any? So there's always a fraction of disordered component in there, or?